In this video, we are going to use Abaqus to model this truss. As you can see, this truss is under two loads, a horizontal and a vertical load. This is the magnitude of the force, which changes over time. It goes from 0 to 10 kilonewton, then to 20 kilonewton, and then down to 0 again. Here are the material properties for the truss, and this is the cross-sectional area, which is 10 centimeters squared. So let's go to Abaqus now to model this truss. So we start by creating the geometry of the truss. It's a 2D part and wire. I'm going to use meter and Newton for the dimensions of the length and force, for the units of the length and force. So approximate size here I use just 20. Continue, and we start by creating the top part from here to here to here, and let's use dimensions. This is 4 meters, and this one also is 4 meters. Now let's go down and dimension it again. This is also 4 meters. And from here to here and here, and we need one more from here to this side, and this one also is 4 meters. Now we can connect this to this, and this to this, and finally this point to this point. Done. So this is the geometry of the truss that we want to create. So this is the same geometry as this one. Now let's go to the next module, properties. We define the material properties. We can put a name for this material like steel, and mechanical properties, elastic. This is only an elastic material, so Young's modulus is 200 gigapascal or 200 E9 Pascal, and the Poisson's ratio is 0.3. Then we need to create sections, so I call this truss bars. The category is beam under truss, and continue. The material is steel that we just created, and cross-sectional area is 0.001 meter squared. All right, and now we need to assign the sections. So we click on this. I don't want to create a set, and then I select all the whole truss, all the bar elements, and then click done. And the section that we have is, we have only one section created. We just created it, so click OK and done. Now we go to assembly. We bring one instance of the part to the assembly, and I'm going to keep it as a dependent instance of the part. And then we go to a step. We create a step. We assume that the load is applied slowly. It's slow, in a way that the inertial effects are not important, so we are going to do only a static analysis on this. So we continue. The time period is 35 seconds because this is the total duration of the load, and we can see here that we need to limit our time increments to 5 seconds in order to be able to capture all these changes in the amplitude of the load. So what I'm going to do, I'm going to go to increment, and initial I'm going to select 5, and maximum also I'm going to select 5, and okay. Now we can go to the load, and we're going to apply the load. Before we apply the load, we need to define an amplitude. So we go here to the tree on the left, right click on it, create. This is, I'm not going to change the name, I'm going to keep it as amplitude 1, and the type is tabular. Continue, and at time 0 the load is 0. At time 10 the load is 10 kilonewton. At time 20 seconds the load is still 10,000 Newton. At time 25 seconds the load is 20,000 Newton. At time 30 seconds the load is still 20,000 seconds and 20,000 Newton, and at time 35 seconds the load is 0. So basically we entered these points on the table. This point, this point, this point, this point, this point, and this point. Click OK. Now we create a load, a concentrated load. I call this vertical load. And the load is applied at step 1, and the point is applied at this point. So done. Now the direction of the load is in the y direction, downward, so it's -1, and the amplitude is taken from the table that we just created. We do the same thing for the second load. So this is horizontal load, and we apply the load here. This time the direction is horizontal, so CF1 is 1 and CF2 is 0. These are the components of the force or the load, and the amplitude is amp1. So okay. So we define the loads, we need to define the supports. So boundary condition 1, which is a pin. We choose displacement rotation, and we select this point that we have a pin acting on it, and we fix the displacement in the X and Y direction. The second boundary condition that we have is here is a roller, but this roller is acting on an inclined surface. So we need to define a local coordinate system which is rotated by 45 degrees and define the roller in that local coordinate system, or in the new coordinate system. So let's go back to Abaqus. We're going to define a new coordinate system. For that, first we need to create a datum point. So let's create a datum point by using the offset. Create datum point by offsetting from a point. So I offset this point because we want our surface to be 45 degree. So if you offset this point by 1 meter in the X and Y direction, that does the job for us. So this is the datum point that we've created. Now let's create a coordinate system using 3 points. I'm not going to change the name here. It's a rectangular coordinate system. Continue. This is our origin. I select this as the origin of the coordinate system, and this point I select it to be on the x-axis, and we need to select another point to be on the xy plane. So that's another point. So this is our coordinate system, the new coordinate system. Now we can go to boundary condition to create a boundary condition, and this is a roller. Continue, and we select this point. Done. And now here we need to change our coordinate system from the global to the new coordinate system that we just selected and that we just created. So we apply the boundary condition in this new coordinate system, and we fix the displacement of this point in this coordinate system in the y direction. So this now is a pin. It's a roller, preventing the movement of this point in a direction perpendicular in the direction perpendicular to the inclined surface, or prevent the movement of this point in the y direction. Alright, so now let's go to the mesh. Since our instance is dependent, we have to mesh this on the part. So if I try to mesh this on the assembly, we're going to get an error message. I'm not going to change it for now to the part. I just want you to see the error message, and then I will change it. So first let's seed this. So we seed the edges. So this is the error message that I was talking about. Basically it says that I have to mesh the part, not the assembly, not the instance in the assembly. So let's seed the edges down. And done. Here we're going to say by number, and we go to 1. We want one element between every 2 joints of this truss. The next part is to assign element type. So if we click on this one and then we select the whole truss, down here we're going to select truss elements. We're going to use truss elements, and for this problem I'm going to use linear elements. So T2D2, which is a 2-node linear 2D truss, is the kind of element that I'm going to use for this one. You can go to quadratic also if you like to have a better approximation, which is 3-node truss elements. Okay, so let's go back to linear, and okay, and done. Now we can mesh the whole part. If you click on this one, and it's okay to mesh the part, yes. So we've meshed the part. If you want to see the mesh, go to view, part display option, under mesh, select check show node and element labels, and you can see the node and element labels here. All right, so we have everything that we need. Now we can create a job. So let's create a job here. I call the job name truss, and the source is from model 1 that we just created. Continue, and I'm not going to change anything here. All right, okay, so let's submit the job. If you right click on this and click on submit, it's going to submit the job, and hopefully it's not going to take more than a few seconds to finish. While this one is running, you can right click on the job and monitor it, monitor the progress. and the job is running. It should show you the steps and the increments, so it showed them all at once, so you can see that the increments are 5 seconds, and basically it starts from 5 to 35 as we requested. So let's dismiss this. The job is completed. So let's look at the results. We right click on this and click on results. So it shows us the results here. So first let's look at the deformation. For example, here if we go to the first step, there is no deformation. Then we can go gradually frame by frame to the next steps, and you can see the magnitudes here. The deformation is exaggerated. We can reduce the scaling factor a little bit to see less deformation here, or to have a better shape of the deformation for the deformation. So I'm gonna use maybe 500. Let's see how that works. It's maybe a little bit low, so I use 1500. So it shows some deformation now, which looks more reasonable. So this is how it deforms. For example, let's now plot the deformation of one of the nodes, for example. So for that we right click on XY data, create, and we're going to select ODB field output and continue. And here we are going to select unique nodal, and let's say we want to have both components of the displacement for one of the nodes, U1 and U2, and here we are going to select the node that we want to plot its deformation. So let's say we want to plot the deformation of this node. So we select that one and then we click on the plot. So here are the deformations. U2 is the blue line and U1 is the red one. So this is how you can plot the deformation of any point or any nodes. Another thing we can do, we can look at the load to make sure that the load is Abaqus has been able to capture the load that we applied, so the time steps were not too big. This was a simple problem. We know that 5 seconds was enough, but let's just check on that. So CF1 and CF2, if I'm going to check the display and the force at this point, so we only CF2 is enough. So again, I'm going to select this node and plot it. So you can see that Abaqus has captured the whole load history correctly. You can try in the step and use a larger maximum time step here. You can try with 10 and run this whole simulation again and plot the force or displacement and see how things change. So let's go back to visualization one more time. So this is the displacement contour plot. We can look at the stresses. For stresses, let's look at S11. Again, you can start from the first frame or the first time step and then gradually move forward to the last one, and these are the basically the steps that you saw, where the stresses during each time step on each element of this bar. One more thing you can do, if you go to the results option and bring this to 0, then you get a uniform stress contour plot in each bar. So that's a little bit more realistic for this kind of problems. All right, thank you for watching this video.